So in the last video, we basically reached the conclusion that I wanted to get to for this little set of videos, where we determined that the pressure of our ideal gas was equal to the gas density times the root mean square speed squared divided by 3. We accomplished this by taking our results from the third video and recognizing that once you allow the particles to move in any direction, that, for like this left wall here, where the pressure is only dependent on the x directional velocity, we somehow needed to convert our total velocity into just how much x directional velocity is that. And because we had a large number of particles and this was an effectively random distribution of the velocities, we could determine that if we took the mean square of our total velocities, divided that by 3, we would get the mean square of our x directional velocities, right? Just a fact of randomness. And from there, we were able to get our pressure. So now, for the sake of completeness, I want to talk a little bit about the ideal gas law, and we're going to just introduce it as an experimentally proven fact, right? That's this little asterisk here. Technically, you can prove the ideal gas law through, more like first principle techniques. But we will treat it just as an experimentally proven idea. Okay. The ideal gas law relates the pressure and the volume of a gas to the number of gas particles and the gas's temperature. Kb is simply a constant called the Boltzmann's constant. So, knowing what we figured out in the rest of these videos about the pressure of an ideal gas, what is the temperature for a monoatomic gas? All right. So all we have to do is sub in our pressure and go from there. So let's first isolate our temperature, which would be PV over N times Kb. And our pressure, of course, was rho times VRMS squared divided by 3. So we have this guy times V over N Kb. Let's go ahead and remind ourselves that density is simply equal to the total mass of our gas, which would be the mass of each particle, little m, times the number of particles, big N, divided by the volume of our container. So we make that substitution, and we can see that the N's will cancel and the V's will cancel, and we'll be left with V RMS squared, little m times V RMS squared divided by 3 Kb. I'm going to write this suggestively as 2/3 Kb times 1/2 m times VRMS squared. This guy is simply the average internal energy of our gas. I'll call this U is the internal energy. Right? And we also recognize that this internal energy is purely kinetic energy. That's not always the case, but in many situations, your internal energy is purely kinetic energy. And right, so this was just equal to T. So another way that we could write this, we could isolate our internal energy So our internal energy is just equal to 3/2 kBT. So from this, we can see that temperature is really a measure of the average internal energy. That's what temperature is. Cool. So why did I say this was purely for a monoatomic gas over here? And how would we generalize this idea for, any gas? And so for the monoatomic gas case, that would be a situation where you have 3 degrees of freedom. What's a degree of freedom? A degree of freedom is basically a direction that can store energy. So what do I mean by that? Well, if I have 3 axes, if I have a gas particle, right, and it's moving some direction, v, I know that at the end of the day, I can break v up into a Vx component, a Vy component, and a Vz component because I'm moving in 3 directions. So the degrees of freedom for this system would be equal to 3. I'm going to go ahead and call this term alpha. And so in fact, our average internal energy could be more generally written as alpha over 2 times kBT. This is a result from something called Equipartition Theorem, which I'm not going to go into too much detail for, just because the goal of this video is to talk about pressure, not go into all the details of gases and temperature and all of that. But yeah, I don't want to go too much into all of this detail about gases. But that's just one way that we could kind of apply our pressure and think about it alongside the ideal gas law. So with that, I hope you enjoyed this little set of just talking about ideas, building up to valuable conclusions like the one here, and kind of a slower step-by-step pace. Again, thank you so much for watching.